This 3 by 3 matrix represents a linear transformation from three-dimensional space to itself. And you've already seen how you can use matrices like this to do calculations. The only trouble is that calculations can be very tedious, especially if you get a bigger matrix with more rows and columns. This particular matrix has got a couple of zeros in, and that's certainly a help. And you'd think that the more zeros you've got in a matrix, then the easier it will be for calculation. The only trouble is that on the face of it, you'd think you're given a matrix and that's the end of the affair. You've just got to calculate with what you're given. But remember, every matrix represents a linear transformation. And so perhaps we might be able to choose a different basis for the transformation and get a simpler matrix. For example, supposing this matrix were calculated with respect to the standard basis in R3, then we might actually choose a different basis. Instead of the standard basis, choose a different one, and then we'd get a different matrix. And we might get a matrix as simple as this one. You see, this matrix is diagonal. All the entries that aren't on the main diagonal here are zeros, and that's a particularly easy matrix for calculations. The question is, can we always find a basis like that which will diagonalize the matrix? Well, you know that by making separate changes of basis in the domain and the codomain, you can get particularly simple forms for the matrix. But what we're going to do is to impose a condition. We're going to insist that we have the same basis in the domain as we've got in the codomain, because often that's what you just have to do in practical problems. If you do that, then it's not always possible to find a basis which diagonalizes the matrix. But there is a special class of matrix for which it is possible, and they're the symmetric matrices. Now, this matrix here is symmetric, and what I mean by that is that these numbers below the main diagonal are just mirror images of the ones above that diagonal. You've got a -3 here and a -3 there, a 4 there and a 4 there, and so on. And as I've said, for symmetric matrices, you can always find a basis for diagonalization. And that's what we're going to look at today. We're just going to see how that works and why it works. But before we tackle the 3 by 3 case, let's look at the simpler 2 by 2 case. Here's Robin.
Well, here's a 2 by 2 symmetric matrix, and you can easily see that because these two elements are the same. And because it's a symmetric matrix, we know that we can diagonalize it. In fact, the diagonal matrix that we get is this one here. And in order to get it, the basis that we have to take is this basis. But of course the question is, how do we find this basis? And to answer that question, we've got to go back to our original definition of a matrix. Remember, the columns of a matrix just represent the images of the basis vectors. So the first basis vector gets mapped to 6 times itself, plus twice the second basis vector. And the second basis vector gets mapped to twice the first, plus 3 times the second. Now suppose we've chosen a different basis. Then the images of these new basis vectors would have been different, and the corresponding matrix would have changed. Let's see what happens as the basis rotates. The images move and the matrix changes. But look what happens when the basis vectors point in these directions. Now the image vectors are in the same directions as the basis vectors, and the matrix is diagonal. So that's the clue. Whenever we have a diagonal matrix, then each basis vector gets mapped to a multiple of itself. And we have a special name for vectors like that. We call them eigenvectors. The name eigenvector comes from the German word eigen, meaning own, because each vector like this gets mapped to a vector in its own direction. Well, in fact, what we do in practice is to do things backwards. We start with our original matrix, and then we find the eigenvectors, and then we use these eigenvectors as our basis vectors. So let's see that in stages. If we start here, then the image is in a different direction, and so this isn't an eigenvector. But if we rotate the vector, then the image changes. And in this case, it's in the same direction as the original vector. And so this direction does give us an eigenvector. And since the image is 7 times the length of the original vector, we say that the corresponding eigenvalue is 7. And here's another eigenvector. It's at right angles to the first one, and this time the eigenvalue is 2, because the eigenvector is mapped to twice itself. So if we choose these 2 eigenvectors as a basis, then the matrix becomes this. There are eigenvalues down the diagonal and zeros everywhere else. So what have we done? Starting with our original matrix, we found an eigenvector corresponding to the eigenvalue 7. Well, here's the corresponding equation. This eigenvector gets mapped to 7 times itself. And similarly, for the eigenvalue 2, this eigenvector gets mapped to twice itself, as you can see. And if we take these 2 vectors as our basis vectors, then we've got a basis consisting entirely of eigenvectors, and so we get a diagonal matrix. And in general, whenever we have a 2 by 2 matrix and we have 2 eigenvalues, then we can get a diagonal matrix. But this raises the next question: can we always find 2 eigenvalues? Well, for a general 2 by 2 matrix, we might not be able to, and there's an example of that in the text. But in this program, we're only concerned with symmetric 2 by 2 matrices. And in this case, we can always find 2 eigenvalues. Let's see why that is. Here's our eigenvector equation. The eigenvector gets mapped to lambda times itself. And we've got to find out the possible values of lambda. And what we do, you've already seen this earlier on in the text, we subtract this vector from both sides. On the right-hand side, we get the 0 vector, and on the left-hand side, what we get are these minus lambdas appearing on the diagonal. Now, if you look at this equation, you see we're mapping a non-zero vector to a 0 vector. And what does that mean? It means that the determinant of this matrix must be 0. This determinant is equal to 0. Well, you can calculate this determinant, this times this minus this times this, and we get this expression here. And as you can see, it's a quadratic equation in lambda. It has 2 roots, and of course their lambda equals 7, and lambda equals 2. Now the question is, can we do this for any 2 by 2 symmetric matrix? Can we always get 2 eigenvalues? Well, let's see. We'll start off with a general symmetric 2 by 2 matrix. Notice that these elements are the same. And as before, we take this vector and subtract it from both sides, giving us the 0 vector here, and on the left-hand side we have this. Just as before, we're mapping a non-zero vector to the 0 vector. And what that means is that the determinant of this matrix must be 0. This determinant equals 0. We can then calculate this determinant in the usual way, and what we get is P there, R there, and Q there. Again, we get a quadratic equation for lambda. And this quadratic equation has 2 distinct roots. Now, why is that? To see why there are 2 distinct roots, and therefore 2 eigenvalues, we have to look at the graph of this quadratic. We'll start with the expression we had before, and this is its graph. There are 2 distinct real roots where the graph crosses the horizontal axis. This is what happens if we vary q. Subtracting q squared pulls the graph down when we increase q, and so there are still 2 real roots. But what happens if q becomes negative? Well, q squared is still positive, and so the graph is pulled down again. In fact, the graph is highest when q equals 0. But now what happens if we change p? Or if we change r? There are still two distinct real roots. And the only time we get something different from that is when p equals r. And then we get two equal roots. But if p is equal to r, and if q is 0, then we've got a diagonal matrix anyway, so we don't need to worry about eigenvectors. But in all other cases, then we get two distinct eigenvalues, as we saw from the graph. So to sum up, any 2 by 2 symmetric matrix can be diagonalized given a suitable choice of basis.
Well, that really is a major step, because now you see we've completely sewn up the 2 by 2 case for symmetric matrices. Given any 2 by 2 symmetric matrix, we can now calculate the eigenvalues, and we also know how to calculate the eigenvectors. But you may still be worrying just what this got to do with some of the work you may have been doing recently about change of basis, transition matrices and all that. Well, these two matrices, A and B, are related by the usual formula that you have for a change of basis. B is P inverse AP. The only slight difference is that instead of Q inverse AP, we've just got the same matrix on either side here, simply because we've got the same basis in the domain as the codomain, so we have the same transition matrix. The matrix A, we can work out the eigenvectors. For the particular case I just showed you, they turn out to be these. Now all these root 5s, don't worry about those. They're just there to make the length of the eigenvector equal to 1 in each case. Now, you can always do that because any multiple of an eigenvector must itself be an eigenvector. So in particular, you can always choose an eigenvector to have length 1. And that's what we've done in this case. So the columns of this matrix P are just the eigenvectors of the matrix A. And there's something else that's special about that matrix that's worth noticing. If you look at these columns, they're orthogonal. The dot product of that column with that column is 0. You see, that times that plus that times that is equal to 0. And that's not a fluke, because it always works that the eigenvectors of a symmetric matrix are orthogonal, and you can actually prove that in general. So what have we got then? We've got this rather special transition matrix. The columns are orthonormal. Any matrix like that with orthonormal columns is given a special name. It's called an orthogonal matrix. So this transition matrix, P, is orthogonal. And orthogonal matrices have all sorts of interesting properties. But there's one property in particular that I want to draw your attention to, because we're going to be needing it. And it's to do with the fact that A is a symmetric matrix. If you go back to the matrix A in particular, you remember we started with the matrix A, which was symmetric. We ended up with the matrix B, which was diagonal. But the particular point I want to make is that it's symmetric. Perhaps in a rather trivial sense, because all the off-diagonal terms are 0, but nevertheless it's symmetric. And it turns out that that's always the case. If you've got two matrices, A and B, related by this formula for transition, where P is an orthogonal matrix, then if A is symmetric, it must be the case that B is symmetric. So in that sense, orthogonal matrices can be thought of as preserving symmetry. And that's going to be an important idea that we're going to need shortly. So let's push on now and return to the original case that we posed, the diagonalization of a 3 by 3. And what we've got to do is to build on the ideas we've used for 2 by 2 matrices.
So let's imitate what we did in the 2 by 2 case. Here's our eigenvector equation. Our symmetric matrix sends this eigenvector to to lambda times itself, and we want to find the values of lambda. And we do it just as before. We start by subtracting this vector from each side, so that here we have the 0 vector, and on the left-hand side we have minus lambdas down the diagonal. Now this matrix is sending a non-zero vector to the 0 vector, and what does that mean? It means that the determinant of this matrix must be 0. This determinant is equal to 0. And we can now work out this determinant. It's rather tedious, but what we get is this equation here. And the important thing to notice is that it's a cubic equation. It starts off with the term minus lambda cubed. And that term comes from multiplying minus lambda, and minus lambda. So we have a cubic equation, and if we plot its graph, then we get this. And notice that there are 3 real roots, giving us 3 eigenvalues. And in fact, the corresponding eigenvectors will then give us our orthogonal basis. So that's what happens for our particular case. Does the same thing happen for a general 3 by 3 symmetric matrix? Well, let's find out. Here's a general 3 by 3 symmetric matrix. You can see it's symmetric because these elements are equal in pairs. And we have the eigenvector equation just as before. We want to find the values of lambda. And in fact, what we do is to go through exactly the same procedure we've already seen. We won't worry about the details. The important thing is that we end up with this equation here. A, B, and C are constants. They're just numbers which arise out of the calculation. But as before, the important term is this first one, minus lambda cubed. We get that by multiplying the minus lambdas down the diagonal. So we have a cubic equation. What does its graph look like? Well, let's have a look. When lambda is very large, then this term will be very negative. So the graph goes down to the right. On the other hand, when lambda is very negative, then this term is very positive, so the graph goes up to the left. So somewhere in between, this graph must cross the horizontal axis. What that means is that we always have one eigenvalue. We may have more than one eigenvalue, but in fact all we need is just one for the time being. And if we've got one eigenvalue, that means that we always have one eigenvector as the basis vector. Well, to see how that helps us, let's go back to our particular example. These are the original basis vectors, and this is the matrix. Let's now rotate the basis until just one of the vectors is an eigenvector. The matrix hasn't been diagonalized, but it's certainly been simplified. And if we now rotate the basis again, then we can diagonalize the matrix. So that's the clue. Remember the halfway stage where we'd rotated the basis just once? And the first basis vector was an eigenvector. So what does that tell us about the matrix? It says that the first column of the matrix must be a lambda followed by 2 zeros. But remember that Norman told us that whenever we've got a symmetric matrix and we apply an orthogonal transformation to it, then the resulting matrix stays symmetric. So what does that tell us? We've got 2 zeros down there, so we must have 2 zeros up here as well. And what can we say about the other 4 entries? Well, the whole matrix is symmetric, so these 4 entries must form a little symmetric 2 by 2 matrix. But we know that any 2 by 2 symmetric matrix can be diagonalized by means of an orthogonal change of basis, and that's going to help us diagonalize the whole 3 by 3 matrix. Let's see how that goes. This is how we started, by finding one eigenvector. Now keep this eigenvector fixed, and what's left is a plane containing the other 2 basis vectors. If we just think about that plane, then the transformation is represented by this 2 by 2 matrix. We can diagonalize this matrix by rotating the two basis vectors in the plane, keeping our original eigenvector fixed. And that gives us 3 eigenvectors in our basis. So we can diagonalize not just the 2 by 2 matrix, but the whole 3 by 3 matrix.
And that was very cunning, because although we started with a 3 by 3 matrix to diagonalize, the way we approached the problem was to reduce it to a 2 by 2 matrix, a problem we already knew how to solve. And that's the secret to the general approach, to the problem of diagonalizing an n by n symmetric matrix. Because the general method of proof is induction. You show that if you can diagonalize an n-1 by n-1 symmetric matrix, then you can do it again by adding another row and another column. You'll see the details of how that's worked out in section 5 of the unit. And there we actually complete the proof that you can diagonalize any symmetric n by n matrix.